So I just was doing some coding. I actually haven't really sat down and been able to bang code in a while, but I was transferring some stuff from old stuff from procedural to OO, and I hate OO. God, I hate OO. And it occurred to me what the pattern was that I had been missing, that I had been disturbed by all these years. What you're doing with object-oriented style calling with code is the following. You are allowing the coding style where you have limited scope globals. Okay, so a class defines a scope where you can use global variables more easily. Now, this has a neat feature, which I'm actually, sort of warming up to, kind of, even though I think OO is Satan, where you can pass fewer variables because you can say, oh, well, all this stuff is globally scoped. That's very handy if you do good design. Good design's impossible, by the way, for most people. So, like, this is why OO failed. There's lots of articles on the web. They're 10 and 15 years old in some cases. Why OO failed the entire market. I agree. It certainly did. There are good reasons for that. There's lots of things to go into with OO. The UML to code idea that's been around since the 70s, that has been failing since the 70s. There's all sorts of reasons why OO fails. And also things to recommend it. Like, yeah, I mean, it gets close to UML straight to code in theory, just in practice. It doesn't, because all the hard parts are hard. When you change the scope, when you look at that, you say, well, what did they do in the old days? Did they just pass globals around wholesale? Well, it occurred to me, yeah, we did in basic. Basic programming, that's exactly what you do. You just have way more global variables because you don't want a lot of return codes. In fact, you can't have lots of return codes in BASIC. It's not possible. So you rely very heavily on variables. That doesn't happen in C, right? So in C, the way you solve the scoping global problem, where you have global variables that are just within a scope, as a class is in OO, is either you put them in the same file or you make them part of the same link set. If you know how to use the linker and you understand the 4-stage compiling process and all that nonsense, it's not really nonsense, but it is hard. I happen to understand most of it pretty well. Didn't ever get around to writing a 4-stage compiler, various reasons, whatever. Jonathan Blow's got a great video he did with his buddy Casey there recently. It was a live stream on Twitch that they put on YouTube. Maybe I'll link it to this if I can possibly remember. I don't put a lot of effort into these videos. You want to see videos with effort? Go to Navigating Patterns. That's my better channel. They were talking about compilers and how people make it voodoo magic, and it turns out it's just two different tree procedures. And with two different tree procedures, you can drive everything. And that's actually true. I'm not 100% sure because it's been too long since I read it, and it's in the damn shed. Compiler design in C by Holub, I think, has that concept down. Now, they're still using Lex and Yak, which Jonathan Blow complains about, maybe rightly, although, man, it's really easy to build stuff with that, with those tools. It's harder to build those tools. I've built most of them. I've never built a linker. It's correct that you just need a left tree and a right tree parsing function. That's it. Like, you can really do the whole thing with that pretty much. I mean, there's some exceptions to that. It can get a little hairy when you're looking at things, but ultimately that's all you need. And there's certainly better ways to do language compilation. But at the end of the day, what OO gives you, that scoping in the file, you can do that in C by grouping different files together and doing it in the link stage. And people don't know that because C is hard. And there's a lot of aspects to C that are not variables and recursion. Like, how does your linker work? What link chunks do you put together? A lot of this stuff is kind of esoteric, even to good C programmers. They don't actually know that that's an option or how to use it, because there's lots of ways around that. One of them is make everything a global, right? Pound defines can get you around a lot of this stuff too. Macros can get you around a lot of this stuff too. There's lots of solutions in C. That's one of the problems with it. You can shoot your foot off in any number of ways with C. In C++, it's unavoidable that you're going to cut your foot off, usually with a dull spoon, which is why I don't like C++ at all, although there were some really nice features in there. And if you just take the really nice features and stick to C, or maybe go with Objective-C, which is clearly the best version of object-oriented C that you could possibly come up with. I defy you to come up with a better way. I don't think anybody ever could. I don't think it's mathematically possible. Objective-C is gorgeous. I've done almost no programming in it, much to my shame, but it is beautiful. Interface Builder is an amazing product. The next development system is unbelievable. But there is a progression from the complication. I've talked about this in previous videos on this channel, right? The complication is moving, right? The complexity is moving. Okay, so we have complexity in compiler linker stage stuff, right? With some complexity in the files and the file structure, and then we compress that down to kind of a flat file structure, and linking and all that's kind of handled automatically for you in the OO languages, right? And then you solve the scoping problem by putting it in these classes, so the complexity is moved into the files, and maybe that's more understandable. Like, I'm not going to make a religious case here, right, on C is better than OO programming languages, because I'm not going to do that. I'm not going down that route. I'm just saying there are different ways of handling the thing, and you can see the complexity moving. And then now you get a more interpreted language. Well, interpreted languages handle this in very much the same way. That's why most interpreted languages, like Java is an interpreted language, right? It's bytecode compiled, so it's half interpreted and half compiled effectively. They usually support multiple programming styles, right? Because you can't support multiple programming styles in a compiled language quite as easily. You can, it's just not as easy, right? It's how much work you make the compilers do. And making compilers do work versus making processors do work has been a theme throughout the computer industry for years. The easiest way to see this is to look at CISC versus RISC, and then look at CEL from IBM. So the CEL, the sales pitch on the CEL processor unit was, because of what we're going to do, effectively what they're doing is they're using power chips. They're front-ending RISC-like, although more CISC-like processors on top of multiple mini cores, right? They're not GPUs. It's not fair. They're like GPUs. They have shared memory, and then there's multiple little processing cores, and then they have caches, right? So I think it's a 4 cache system, maybe 3. I forget. I ignore their designation of caching. I'm using it more technical. Where's the memory, right? So they might not say they have L1, L2, L3, L4, but if you look at the system, they have 4 different speeds of memory. That's 4 caches. Right, or maybe it's 3 caches and 1 main memory, whatever. I think they have 4 internal high speed on chip memory, different speeds on chip memory with different interconnects. But be that as it may, there's some level of caching. And then the CEL was, we're going to fix the compiler to make the code fast, because the compiler is going to interpret your code and just spit out the right code on the back end. Right? And all compilers do this, right? But that would be really fast. And the problem is that doing that is really hard. If you want to know how hard it is or why it's hard, you can read up on pthreads in C, right? Threading in C, and I've done that. I've written threads in C. I've written them with pthreads. I've written them sort of pre-pthreads, because pthreads is relatively new. When I learned C, there was no pthreads, didn't exist. ANSI was brand new the first time I used C. So the ANSI standards. So what you see is there's different ways to do threading in C. Pthreads is a non-trivial problem. And then you see how that connects to something like Go. So the promise of Go is, well, we just figure out how to parallelize. What's parallelization? It's threading. That's parallelization and threading, the same thing. Right? Threading is a form of parallelization. It's not all of parallelization. You can do parallel things without threading. But you see where that complexity, where that fight is. Where's the complexity? Is it in the chip? Is it in the programming language? Is it in the compiler? Right? So are you putting the burden on the programmer to know how to do the threads manually like you would in C? And then you can simplify that with pthreads. Granted, sure. But then, are there really threads? And they changed threads to lightweight threads, and they've got thousands of designations of threads now. It's kind of foolish, if you ask me. Threads carry scope with them, though, guys. They carry scope with them. And that's actually really important. And so it turns out that, yes, you can make very efficient threading. The problem is when the overhead of the thread or the global scope of the thread is larger than your caches, you're actually not doing yourself any favors performance-wise. And so effectively what I'm telling you is you're better off hand coding this anyway if you need speed. Almost nobody needs speed because hardware's gotten faster and faster and faster, although that plateaued a while ago and no one noticed. Different argument. And that's not because of chip speed, it's because of bus constraints. After the Pentium 90, after the Pentium 90, the single largest constrainer to performance was bus speed. And it has been ever since. And that's why for a long time, Sun dominated the workstation market because they had the crossbar switch and they had a patented crossbar switch and it was freaking awesome. Sun machines had very high bandwidth. They were excellent workstations, also hugely expensive. Also why they went RISC first, right? And Intel went RISC and failed immediately for lots of good reasons, aside the fact that Intel's the worst chip designer that's ever been on the planet and continues to be the worst chip designer ever on the planet. So what you end up with are weird things like Sun is the first to the container market. Why? Because it just turns out that optimizing for RISC, which like Sun machines had 30 core, Sun had 30 core boxes in the 90s. Like they were doing multi-core boxes in the 90s. Very fast stuff. It just turns out that in order to squeeze the performance out of that, you need something like containers. You need some form of virtualization. We talked about this before. There's 3 forms of virtualization. Containers is a top level OS managed form of virtualization. It's also the slowest and probably the dumbest in most applications, unless you're doing certain specialized things, which Sun, of course, was good for. And also Sun grew out of the one large computer, several smaller workstations model, where containerization is great. Fantastic use model for containers. Everything else is a bad use model for containers, by the way, or almost everything else. So you can see the complexity sort of moving around and the industry struggling with these concepts of who does the optimization? Is the optimization done by the programmer at the time of writing the code? That's what should be done because it just turns out the smartest computers in the world are still you, or at least collective programmers or something. How much and what of the work for optimization is done by the compiler, and how does that affect your chip design? Because a lot of chip design is actually done for speed to help the programmer, but not all of it. Like the whole purpose of Cell was to simplify the you simplify the die design, you get the yields up, that gives you more profit, right? But if you don't fix the compiler, it's too hard to program for because effectively you end up writing machine language, right? Or something close to it. Like you don't want to, you think machine language is bad. Try to code a machine language in RISC. Like I'm sure that I haven't looked. I'm sure there's an example out there somewhere of like the sheer number of commands to do the same operation CISC to RISC in machine code, right? Or assembly language or something. It's nuts. That's why the DEC Alpha design is still the best chip design ever conceived of by mankind and will remain that way forever. The microcode back to the RISC, you've added another layer of optimization where your microcode optimize your RISC processor. So you have CISC instruction set, the chip, the hardware does the work, although it's really firmware because it's programmable, right? It's kind of like a programmable GAL or something. I don't even know how that stuff works. We're in hardware land where I know the least. So that does the translation into the RISC, into the efficient RISC, and does the pipelining. Pipelining is the same as threads, right? Ultimately, right? That's why when they talk about cores and threads, hyperthreads, that's the same as doing it in software. It's just the hardware is doing the threading for you from the software commands. You can do that more efficiently in microcode and keep the RISC and increase the cores, or at least decrease the pipeline size, but increase the number of pipes, at least in theory. There's limits to all this, of course. But that's why the DEC Alpha was so fast. It was a very efficient chip. I have some DEC Alphas in the shed somewhere. They're awesome. They're really fast for how slow they run megahertz-wise and the bus constraints. They're super fast chips. So you end up seeing, okay, so there's threading, parallelization, however you want to think about it. And then there's all this optimization going on. Do you optimize at the hardware layer, how much do you optimize at the hardware layer? How much do you rely on the compiler? And how much do you rely on the software engineer? And how much do you rely on the programming language? And so all of these are sort of feeding into each other. And it just sort of came to me, that full outline just came to me just now while I was dealing with this code that I translated, like I said, from functional to OO code for reasons I'm still not happy about. I had working code until I had to translate it into this garbage. But to be fair, yeah, I actually kind of like the fact that I don't have to use large return, don't have to pass large return values. They're not large in my case, it's a small piece of software, but I don't have to pass lists around, right, as return codes, because I can just use in-scope globals, which is effectively what a class is. It defines your in-scope globals. So once I started thinking about it that way, I'm like, oh, okay, this isn't the worst thing in the world. I see why people like it, even though I think it should burn to the ground and everybody involved should be cast out into the bowels of hell. Different problem. So I just wanted to share that with you. Hope you found it helpful. I know these are always a little rambly, but if you get comments or questions, leave them below.